Hello viewers, welcome to my channel PC Geo Kimberlite, a source of diamonds. Today on the special demand of Sandy, I am preparing a video on optics, interference phenomena and optic science. I thank Sandy so that after a long back I have been refreshed my knowledge and prepared the videos, and within a very short period of time I'll complete the optics. I thought I can start with the basically the right from the basic course of mineralogy, then slowly come to the optics. But on the demand of Sandy, I have to start directly from the optics. So no doubt we will complete, then we'll go for the rest what we have the mineralogy. I'm Dr. Sajid Hundekar, Associate Professor and Head, Department of Geology, AKI, Pune College of Art, Science, Commerce, Camp Pune, India, Maharashtra. It is affiliated to Savitribai Phule Pune University. It is simply called as SPPU Pune, and formerly it is known as University of Pune. Yes, now the very important one, interference phenomena and optic science. You have to remember certain concept to be remembered. I'm not here start with the basics of what microscopes are there, what are the various parts are there. I have already uploaded two videos on the optics, that is the optical properties of mineral in plane polarized light, the seven properties. Then again, the next video I had done it, identify the optical properties under play of cross Nicol or analyzer. So there I have been detailed discuss about the petrological microscope. Those who are interested, they can go and check it on my channel. Just we'll start with this, that the optical mineralogy involves studying minerals as well as rocks by studying their optical properties. We have to make the thin sections, and earlier one it is take the 70 hours. Now we have new techniques have been come out. Now we can prepare, but the thickness has to be a very important one. Today, most optical mineralogy involves examining thin section with petrological microscope. Light entering a crystal may be refracted or reflected. Petrographic microscope have polarized light source that illuminate a thin section, because polarizer, the lower prism is always there. So the light coming from this polarizer is 100% vibrating in plain polarized light. But once it is coming out from the polarizer, 90%, but there will be above that the condenser is there, and that condenser completely filter rest of the light which is vibrating in a different direction, and the light which is coming out from the polarizer, it is 100% plain polarized light, and it is incident on the glass media where we have been on the Canada balsam, the middle mounted is there. So the air media to the solid media, the light will be what is happening, double refraction has taken place. One ray we called as ordinary ray, and second one we called as extraordinary ray. So ordinary ray is constant one, extraordinary ray at one few places it faster, and few places it will be again matched with the ordinary ray. So elongated or oblong shape will be there about that. The extraordinary ray, to we examine thin section in two modes, one plain polarized light as well as cross Nicol. That properties I have already made the two different videos on it. In plain polarized light we can discuss the opaque and non-opaque metals. We can see crystal shape. Yes, when you are going to see in plain polarized light, what we are going to see, crystal shape, habit, cleavage, color, pleochroism, relief, twinkling. That we are going to see that seven properties. That is the color, form, relief, cleavage, crack, then twinkling, and then we have pleochroism. Then similarly, once you upper Nicol insert, then the shortest axis of the polarizer and the shortest axis of the analyzer are cross. And when you're going to study in this particular procedure, then we are going to see those mineral completely dark throughout the rotation. We call them as a isotropic, and those in between giving you colors and darkness at four places they become dark, and in between these four places we are going to get the colors. So that is the anisotropic mineral. and the rest of the property we are going to study in anisotropic mineral. In that we are going to see isotropism, anisotropism, extinction, twinning, then the cross hatching, interference color, turbidity, and the distinction property. Then we have the identified. So this is the way we are going to see the properties in plane polarized light and the properties in cross Nico. In the cross Nico, in the cross polarizer light, we discuss anisotropic from isotropic middle. We see interference color related to birefringence. That is the already we have in talk now. We use cross-polarized light to learn a crystal optic classes and its optic sign to measure the extinction angles or sign of elongation or to measure the 2V. A combination of optical properties allow us to identify mineral in thin section and to interpret geological histories. Now, introduction to the mineral optics. Optical mineralogy involves studying rocks and minerals by studying their optical properties. Some of these properties are macroscopic, and we can see them in mineral hand specimen also. But generally, we use a petrological microscope called as polarized microscope, and the technique is called transmitted light microscopy or polarized light microscopy, that is PLM. A fundamental principle of PLM is that the most mineral, even dark colored mineral, and other that appear opaque in hand specimens light specimen transmit light if they are thin enough. In standard petrological microscope, polarized light from a source beneath the microscope stage passes through samples on the stage, and then you are going to see on your eyes. That is the way you are going to transmit. At the largest level, we divide mineral into opaque minerals and non-opaque mineral. Opaque mineral will not transmit the light unless the mineral grain is much thinner than the normal thin section. We further divide non-opaque mineral into those that are the isotropic, having the same properties in all the direction. When you rotate the rotating stage in the under the analyzer, we will find out that throughout the 360 degrees, the intensity, the quantity of the darkness will remain same in a one state than the isotropic, and those changing the colors, darkness, shades of colors you are going to see, these are the anisotropic. Finally, we divide anisotropic mineral into those that are uniaxial and biaxial. Once you get the anisotropic mineral, we have broadly been categorized into them into uniaxial and some of them the biaxial according to whether they have a positive or negative sign also. Now, optical classification of minerals. Mineralogists often classify mineral according to mineral optical properties. The table below shows the basic classification scheme and gives example of mineral belonging to each of these six categories. At the highest level, we divide mineral into two groups, opaque minerals and non-opaque minerals. We further divide non-opaque mineral into those which are the isotropic and anisotropic. Then we divide anisotropic mineral by their properties. Yes, here we have one opacity, isotropy, optic class, optic sign, and example of mineral. Opaque mineral: gold, copper, pyrite, pyrrhotite, magnetite, illuminate. These are the opaque one. And non-opaque, in this category we are divided into isotropic and anisotropic. In the isotropic, garnet, diamond, halite, fluorite, periclase, and spinel. This comes under this category. Then in anisotropic, we have again uniaxial and biaxial. So in the uniaxial, positive sign quartz, zircon, ice, brucite, rutile, and lucite. Whereas negative uniaxial mineral, apatite, calcite, beryl, tourmaline, and corundum. Whereas in biaxial, positive minerals are enstatite, diopside, sillimanite, gypsum, and plagioclase. Whereas biaxial negative mineral which are there, K feldspar, muscovite, hornblende, plagioclase, and epirote. So this is what we have. Optical classification of mineral divided into opaque and non-opaque. Non-opaque mineral divided into isotropic. Anisotropic mineral, again isotropic mineral will be divided into uniaxial and biaxial. Again, each one is divided into positive, negative, positive, and negative. So this is the important chart. If you remember the names, then it is well and good. Light and the properties of the light. I am starting from the basic, so you should not have any sort of problem. Taking a close look at the light and its properties, it is very helpful because once you have been starting, then you are going to the higher version. Light is one of the form of electromagnetic radiation. Radio waves, ultraviolet light, X-rays are the forms of electromagnetic radiations. All the consist of propagating, moving through the space, electric and magnetic wave. Hence, they term as electromagnetic. The interaction between electrical waves and the crystals are normally much stronger than the interaction between magnetic waves and the crystal, unless the crystals are magnetic. Light composed of multiple wavelengths appear as one color to the human. If wavelengths are corresponding to all the primary colors are present with equal intensities, the light appear white. Once all intensity are same, we are going to appear as a white. White light is said to be a polychromatic, many colored, because it contains a range or spectrum of the wavelengths. The polychromatic light can be separated into different wavelengths in many ways. When one wavelength is isolated, the light is monochromatic, single color. You can see now here the wavelength is given in NM 400, 450, 500, up to 700. So you can see how this variation, how the waves have been changes is the wavelength. So the different wavelengths and the color visible things have been given. Besides the wavelength, frequency and amplitude, a phase characterize all waves. Amplitude refer to the height of the waves. Yes, you have to remember the common terms which are there. Phase refer to whether the wave is moving up or down in a particular time. If two waves move up and down at the same time, they are in a phase. If not, they are out of phase. When two waves with the same wavelength travel in the same direction, simultaneously they interfere with each other. The amplitude may add or cancel or may be somewhere within. The nature of the interference depend upon the wavelengths, amplitudes and the phases of the two waves. As you can see now here, this is the phase, out of the phase and completely out of the phase. The light wave passing through the crystal can have a variety of wavelengths and amplitudes and phases affected by the atomic structure in the different ways. They yield interference phenomena giving mineral distinctive optical properties. Yes, the wavelength which are there, they will be having same wavelength and they will be in the same direction, then they will in phase. But if there is a fluctuation is there, we'll find out of phase. We are completely out of the phase. Snell's law and the light refraction, that is also here to see now. We have all seen objects to appear to bend as they pass from air into water. For example, if you consider a straw in a glass of soda or an oar in a lake water, seem bent or displayed when you know they are not. We call this phenomenon as reflection. You can see now, a straw has been added, but you can see here that there is we are going to find out that there is the split has been taken place and they have been drifted, but it is not actually, it is not done. Yes, that is the figure 5.10 shows an example of a pencil in a glass water. Refraction occurs when light rays pass from one medium to another. So that is from air media to the water, that is liquid media. So it has been water to the air, it has been gone with a difference of the refractive index. If the light strikes the interference at an angle more than 90 degrees, it changes direction and can distort a view. When refraction occurs, a light beam bends towards the medium with higher refractive index, where light travels slower because one side of the beam moves faster than the others. Consider a beam traveling from air into water. Yes, that is what we have the incident and it is the refracted. Yes, whatever the angle which is made and it is the angle of refracted. Yes, the angle of incidence, you can measure it out in the vertical plane, and the same one when it is a refraction is there, you can measure. So the side of the beam which is reaches the interference first will slow as it enters the water. It sorts of stuff to its toe, so beam bends towards the water. No refraction occur for beam traveling at a 90 degree to an interference between the media and the different refractive indices. Beam follow the straight path. In this figure now, the 5.11b shows that the opposite case, a beam traveling from a media of a high refractive index, lower light wave velocity into another way of refractive index, that is faster velocity. So that has been shown in the examples now. When light reaches an interference between the two different media, the angle between them and between the beam and the perpendicular to the interference is the angle of, so there will be a formula, yes, angle of incidence divided by angle of refraction. Yes, so after the crossing the interference, the angle between the beam and the perpendicular to the interference is the angle of refraction. The relation between them is the angle of incidence and the angle of refraction. It is given over here. Incidence vi, that is nr upon ni. Polarized light. What is a polarized light? The vibration direction of a light wave, which is the direction of motion of the electric wave, is perpendicular and or nearly perpendicular to the direction of the wave. You can see now here, this is what we have. The whatever the light is there, it is a direct. What we have, it have the different directions are there. In normal polarized beam of light, the waves vibrate in many directions. Yes, this is the unpolarized light. You can see the light is vibrating in all different directions. But once you are going to come out through this polarizer, we'll find out the light is vibrating in just a single plane. When we can filter an unpolarized light to make all these waves vibrate in one direction parallel to the perpendicular plane. You can see horizontal, the light will vibrate in a one single plane, light is vibrating in a single plane, then the light is vibrating in the vertical plane. Yes, so these what we have, these are the called as the polarized light. The light is then polarized, sometimes called as just polarized. Unlike the drawing in 5.16, that is what we have done, a beam of light, whether polarized or not, may contain many different wavelengths. Figure 15.6a shows the wave vibrating horizontal. Yes, this is horizontal. The B shows vibrating in vertical one and shows two polarized light rays. The horizontal and vertical come together. Figure shows now, that figures what we have, the 5.17 shows what happened when a beam of unpolarized light encounter a polarized filter. Only two vibration directions are shown for the unpolarized light, but you should envision light vibrating in all directions, but before it reaches the filter. Once it reaches the filter, that filter will take out and completely, this is a filter what we have, and the light will completely come out 100% in a light vibrating in a single plane. After passing through the filter, the light remain unconstrained to vibrate in one plane. It is the plane polarized light. In this figure, the polarization direction is horizontal, but it could be in any direction, whether vertical or horizontal, which will be there, could be rotated the filter. Suppose the light passes through the polarizing filter that constrain and it to vibrate horizontally. In this figure, we only show two of them, many vibration directions in this unpolarized light. That is the unpolarized light. It can come out the polarized light, but think vibration would occur in all directions. On the other side of first filter, yes, here we have two filter, one and the second filter. On the other side, the first filter, the polarized light, although perhaps decrease the intensity, appear the same eye because the human eye cannot determine whether the light is polarized. Yes, this is what first filter, light is filtered, and here also the light has no light now. Yes, that is the way going to make out. If, however, a second polarizing filter oriented perpendicular to the first, the orientation has done in the path of the beam. You cannot easily determine the beam is polarized. If the second filter allows only the light vibrating in a north-south direction to the pass, no light will vibrate. Those light which is vibrating in the north-south, only that comes out, but it is not there. It is a horizontal one, so it will not be come out of that particular part. Yes, the plane polarized light or cross polarized light that we are going to see now. For routine viewing, petrologists, mineralogists use polarizing microscope with orthoscope illumination with or without the upper polarizer inserted. Many times we not use the upper polarizer. Normally, that is the analyzer. We use only the polarizer. Without the upper polarizer, we see a sample, the slide of the mineral or a rock in plain polarized light. With the upper polarizer, we can see the properties in cross polarizer, or this is called as cross polarized light. The optical properties like shape, color, relief, cleavage, refractive index, pleochroism, twinkling also determined using the PP light, that is plane polarized light. We use the cross polarized light, that is the light in analyzer, cross nickel, sometimes focus with conoscopic or Bertrand lens. We can use also Bertrand lens to determine the other properties including retardation, optic sign, and 2V. When polarized light encounter an isotropic mineral, it shows as it passes through the middle, but it maintains its characters when it is imaged. So it is remaining dark throughout when it is isotropic one. Upon entering an anisotropic middle, however, the light is normally split into two polarized rays, each traveling through the crystal along the different path with a slightly difference of velocity, maybe lambda, by lambda by 2 or 3 lambda by 2. So this is the differences of 2 lambda. So that difference, ordinary ray and extraordinary will be vibrating now. For uniaxial mineral, we call the two rays, one ordinary ray and second one is extraordinary ray, E and E or O. That is ordinary ray we mention as O. The incident light is from air media to the solid media. It is refracted now. One is ordinary and second one is extraordinary. The ordinary ray travel path predicted by the Snell's law, while E ray does not. The direction of O ray and E ray vibrations depend on the direction of light is traveling through the crystal structure. But as seen in the figure, the vibration direction of two rays are always perpendicular to each other, or when they emerge from the crystal, yes, they're perpendicular. One is horizontal, one is the vertical one. We call the splitting of a light beam into two perpendicularly polarized light, that is the double refraction. All randomly oriented anisotropic mineral cause double refraction. We can easily observe it when we place a clear calcite. Yes, Iceland par we have keep this one, and below that if we have any rod or pencil dot is there, if you rotate them we are going to get the two dots. Yes, we can easily observe the place over the calcite on a piece of paper on which a line or a dot or other image can be drawn. We are going to get the two images, and one is constant and second one is moving. The two images appear, one is corresponding to the other rays. A thin piece of polarizing film placed over the calcite crystal would verify them that two rays are polarized and they are vibrating perpendicular to each other. If we rotate either the film on the crystal every 90 degree, one ray becomes the extinct and we will see only one image. Calcite is one of the few common metals that exhibit double refraction easily seen without a microscope. But even minerals that exhibit subtler double refraction can be tested using polarizer filter. Gemologists use this technique to tell gem from imitation made of glass. Glass, like all isotropic substances, does not exhibit double refraction. Yes, here we have shown that how you rotate, you can change the direction which has been made. That when a light shown on any direction, what happens? That the something else happens too when the calcite rhomb is rotated. On rotation, one dot remains stationary, other one is rotated. That is going to make out. The stationary light vibrate in the basal plane, and other no matter of degree of rotation always travel the same distance in the same time. This is called as ordinary ray, and the second beam vibrating in the plane of the optic axis travel in the different distances depending upon the orientation. This is called as extraordinary wave. Consider a thin section and the light entering an anisotropic crystal. The double refraction occur as the two rays pass through the crystal. That is, whether it may be uniaxial mineral or whether the light may be the biaxial. They travel at a different velocities unless they are traveling parallel to an optic axis. This is the mineral grain, and this is light which is coming out plane polarized. And now here we have fast ray which has been mentioned, and the slow ray which has been given. So that is the retardation has been mentioned. Because the rays travel at a different velocities, their refractive indices may be different. The differences in the indices in the fast ray as well as slow ray, that is n minus m, is the apparent birefringence which is given. It varies depending upon the atomic orientation in the crystal, and the direction of light is traveling the range from 0 to the maximum value controlled by the crystal structure, and the maximum birefringence is a diagnostic property of mineral. Now come to the next one, uniaxial minerals. Biaxial we'll see as a separate video because here it will be take a long, so I have not been included here as a biaxial, but only we have been restricted to the uniaxial. I'll make the sign of elongation separate, Ri, that also I'll make a separate one because that is there in the practical also, and this is there in the theory also. So theory and practical, if you've done this one, if you understand the concept, then practically if you thoroughly understand the concept, then your theory will be a strong one and you can appear any questions of that particular topics. If a crystal is oriented so that the optic axis is perpendicular to the microscopic stage, light passing through the crystal travel parallel to the optic axis and behave as if the crystal were isotropic. Yes, here you can see a crystal is oriented so that the optics axis is perpendicular to the microscopic stage and the light pass through this crystal travel parallel to the optic axis and behave as it is the crystal were isotropic. There is no double refraction and the polarization direction of the light is not changed by the interaction with the crystal. If we view the crystal with upper polarizing inserted the cross polarized light, the grain will remain extinct and even throughout the rotation. Most crystal in thin section, however, will not have optic axis vertical, and we will see optic properties that relate to the crystal system of the mineral. For example, all minerals that have crystals belonging to the cubic crystal system are isotropic. All minerals with a crystal that belonging to the tetragonal or hexagonal system. Remember, this is very important. All mineral with crystals that belonging to the tetragonal or hexagonal crystal system are uniaxial, meaning that they have only one optic axis, tetragonal or hexagonal. In these crystals, the optic axis is coincident of the C crystallographic axis. Yes, this is the optic axis will be there along the C axis. The optic axes are parallel to the or perpendicular to the crystal faces. In uniaxial crystal, refracted index varies between two limiting values that were designated epsilon and omega. Epsilon and omega. The maximum value of birefringence in uniaxial mineral is absolutely value of the difference between the omega. We can only see maximum birefringence with correspondence with maximum retardation if the optic axis is parallel to the microscopic stage. Light traveling parallel to the single optic axis of a uniaxial mineral travel as an ordinary ray and has refractive index is mu. In light traveling perpendicular to the optic axis has a refracted is the unless the ordinary and extraordinary, that is simply we make it out, unless traveling parallel to the optic axis light is doubly refracted and splitting into two rays, one having the refractive mu and other one has the epsilon, which will vary depending upon the direction of traveling they have, the ordinary and extraordinary wave which are there. We will divide uniaxial minerals into two classes, less than epsilon, the omega, the middle is uniaxial, that is a positive, and when mineral is uniaxial negative, we can use the pole, that is the omega, and the norm, that is negative omega more than epsilon, that is the relation will be there. The positive minerals are often described as having a positive optic sign. Mineral, the negative mineral has a negative optic sign. Now interference figure. To determine whether an anisotropic mineral is uniaxial or biaxial, whether it is optically positive or negative, require obtaining an interference figure. Any uniaxial or biaxial mineral, whether in a grain, mount, or in a thin section, will in principle produce a visible interference figure, and isotropic mineral will not. We must take care to choose grains without crack or those flaws so light can pass through without disruption. In addition, for some purposes, we need grains with a specific orientation. Having chosen an appropriate grain, obtaining an interference figure, it is relatively straightforward. We focus the microscopic using plain polarized light and have high magnification. If perfect focus is ambiguous, it is often helped to focus first at a low magnification. Then we insert the upper polarizer to get the cross polarized light. If the microscope is properly aligned, the grain will still be in focus. Next, we fully open the substage diaphragm, insert the substage conoscopic lens if it is not already placed. Then insert the button lens above the upper polarizer. As seen the figure, the conoscopic lens focuses the polarized light so it enters a mineral grain from many different angles simultaneously and focus on a small area. Double refraction occur for all rays, and different wavelengths having a different retardations as the upper polarizer slow rays and the fast rays combine to produce interference color. Yes, that is a very important how they are going to act on that. And above that polarizer, the button lens focuses the light so it is parallel again. The button lens also magnifies the image, so the two spatial lenses together permit us to see the interference figure and examine the light traveling through a crystal by many paths in a single view. Yes, here we have the light, the polarized light, the conoscopic lens, mineral grain on rotating stage, upper nickel prism is there, Bertrand lens, and you are going to see the interference figure. I can see here again a light, ordered light, then polarized light, then lower diaphragm is there, 100% light will vibrating, then the rotating stage, sample, the slide is there, then here we have objects which are there, and after that we have the upper prism, then button lens, the eyepiece will be there, and you are going to see that particular part. Weaving an anisotropic crystal under the cross polar or analyzer inserted, the crystal is extinct when the either of the two privileged directions in the crystal are lined up parallel to the polarizing direction of the microscope. This is the because when privileged directions are parallel to the polarizer, the crystal does not change the polarization direction and the light will thus vibrating perpendicular to the analyzer. When the privileged directions are not parallel to the polarizer, the light transmitted by the analyzer and this light shows a color and called as interference color because of there is the interference has been taken place between the ordinary and extraordinary. All the work you have done so far in lab has been with the microscope. Array made is called as orthoscope. In orthoscope made, the light incident and passing through the crystal on the microscope stage is perpendicular to the lower and upper surface of the crystal. In conoscope mode, a lens called a condensing lens is inserted between the light source and the crystal. Is focused as the incident light is no longer perpendicular top and bottom of the crystal but crosses within the crystal. Yes, the same diagram what we have done has been mounted here. Yes, that will be the same part will be there what we have done. That is addition to another lens called the Bertrand lens, which has been inserted here. That is the Bertrand lens between the object and the ocular lenses. To put the microscope in the macroscopic mode, you must do the following things. One, you have to do switch to the highest power objective lens 45x. You have to use 45x. Switch in condensing lens located beneath the stage and raise it to the position so that the top is just below the stage. Switch in Bertrand lens located just below the ocular lens. Initially, make sure that the compensator plate is not in. The compensator plate should be of intermediate position. Put the analyzer in. Now imagine and that we have a grain of some uniaxial middle on the stage oriented in a position such that the C optics axis is perpendicular to the stage. Recall from the previous discussion how we could recognize such a grain. It is a grain that shows only the mu refractive index. One shows no relief change upon the rotation, and one can would retain the extinct on the rotation if the analyzer is inserted in orthoscopic mode. If we can find such a grain, we put the microscope in chronoscopic mode and we will see a centered uniaxial interference figure as we discussed below. Yes, how this will be stepwise, you are going to make out the middle in the two or more equal crystal axes lie in the perpendicular to the axis of the different length are called as uniaxial. This single axis parallel to the crystallographic axis, C axis, is also called as the optic axis. Which crystallographic system we are talking about? Yes, when the light is shown down the optic axis, it is behaved in the same manner expected when contracting with the isotropic middle. Yes, you can see now here. This is the done by constructing an interference figure, also known as the optical indicatrix. The light is opaque and the optics, therefore, it is doubly reflected. You can going to get a uniaxial indicatrix. The indicatrix is constructed so that the indicatrix are of the refraction are plotted as a radii that are parallel to the vibration direction of the light. Yes, so here we have the short slow ray and fast ray will be there. The light parallel to the optic axis in the center enters middle and it is not split into two, so passes the straight through. More realistically, you identify a middle grain with no minimal variation in the birefringence. Insert the substage condenser and insert the button lens. Use highest magnification and open the diaphragm. Yes, what we have the isogyres. These are the isogyres, and this is what we have metatopes. And the isogyres will be there. These are the waves which have been vibrating. A center uniaxial interference figure is shown as the diaphragm below. It consists of dark bands that consist of the field of form of a black cross called isogyres. Depending upon the thickness and the birefringence of the middle, one may also see the band of color that form color circles that are concentric with the centers of the cross. These color bands are called as isochromes. Yes, these are the color bands will be there. That is the isochromes are there, metatopes, isogyres. At the intersection of the bar of the cross is the melatope, where the light that has traveled along the optic axis exit in the field area. For a perfectly centered uniaxial interference figure, that is, where the optic axis is exactly perpendicular to the microscopic stage, the cross will not be changed the position on orientation during a 360. When you rotate the rotating stage, whatever you are going to get the indicatrix, it will not shifted now because it is the perfect one. Note that the light that has vibrated parallel to the and direction which will be inserted comes out of the interference figure in a pattern that the concentric to the melatope and the light has vibrated parallel to the extraordinary direction in a crystal comes out of the vibration vibrating in a radial pattern as indicated in the figure above. Yes, ordinary and extraordinary ray will be vibrating in this perpendicular to each other. We have to know that. The order of interference color seen in these isochromes increases away from the meratopes. As the thickness and birefringence of the color crystal increases, the number of isochromes seen in the interference color increases. They are the bands of equal retardation caused by the light entering the crystal at the different angle because of the conoscopic lens. Interference figures of the mineral are very low birefringence like a quartz and feldspar may not show any colored isochromes, but most mineral do. Minerals with a low to moderate birefringence typically show a few isochromes, and interference figure for mineral with a high birefringence commonly show many. You can see now how this variation has been taken place. Isochromes for mineral with a low birefringence, you can see layers are very few light, but the isochromes for a mineral with a higher one and the light ray vibrating directions, and this is what we are going to get actually under the microscope. The uniaxial mineral are divided into those that are positive and negative. When ordinary wave which travel an equal distance in all direction has a greater velocity, the middle is a positive. When ordinary wave which travel an equal distance in all direction has a greater velocity, the middle is a positive. When ordinary wave which travel equal distance in all direction has a lower velocity, the middle is negative. When two light rays are indicative of two refractive index of the uniaxial middle, off-centered now. Off-centered uniaxial figure can also be useful in identification purpose. The limbs which shows that the horizontal or vertical, even the center moves to the faster. The optical sign now, yes, once you insert, the slow ray has been mounted. Now when you are going to see yellow ray which is cross the slow ray. Yes, the slow, that is the slow one. So slow ray of the middle and the slow ray of the slide which crosses together, the middle is positive. Now I can see here the slow ray of the inserted wedge and the slow ray of the middle, they are comes parallel together. The middle is called as negative. This is a very important one. If the middle is optically positive, the north, east, and southwest. This is the quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Remember, this is the way you are going to make out in a clockwise direction. And now, very important one, the yellow dots. If the yellow dots are crossing this slow ray, the middle is positive. The northeast and southwest quadrant of the interference figure turn 2-degree blue become addition will have occurred these in this quadrant. Northeast, northwest, this is the northwest, and southeast quadrant will turn 1 degree yellow because subtraction will have occurred in this quadrant. If one remember when yellow color occurs, note that drawing a line connecting the yellow quadrant with the cross the slow direction in the compensator like the vertical stroke of this plus sign. Yes, this is the slow ray, that is the slow part, and yellow one which comes out and they are crossing each other. Yes, this is yellow dots, they are going to cross this one. So plus sign is going to form. If the middle is optically negative, the northeast, this is the northeast and southwest. Quadrants of interference figure 1 degree yellow became subtraction will have occurred this quadrant, and now they have become parallel to the slow ray. So the middle will become the negative one. The northwest and southeast quadrant will have 2 degree blue because addition will occur in these two quadrants. If one remember when the yellow color occurs, note that drawing a line connecting the yellow quadrant with the would be parallel to the slow direction in the composite like the signal stroke on the minus sign. Finding a grain with the optical axis oriented exactly perpendicular to the stage will show sometime be very difficult. It would be much more common to find one within the optic axis is at a slight angle to be perpendicular to the microscopic stage. Such a grain will be exhibit following properties. It is a grain that shows the refractive index and a refractive index that is very close to mu refractive index. Thus, it will show a small change in the relief change of the rotation. It would be a slow, very low order, first order gray interference color between the extinction position if the analyzer is inserted in the orthoscope. Such grain would be so an off-centered optic axis as shown in here. On rotation of stage, melatope would rotate in a circle around the periphery of the field of view and the bar could be isogyre would remain. Yes, as you rotate, it will shift. Yes, now here we are going to get real reverse L. If you make out, it will go turn it out. That will change the position. Go on at four different positions. Even with off-centered interference figure, optic sign can be determined because one can keep track of isogyres and still divide the figure into the quadrants. Again, with the optically positive equal all north, east, and southwest. You can see now yellow one which has come out here. So positive will be there, and this is again positive, positive. This will be, and this is again positive. So what you're going to make out? The turn blue and the northeast will yellow. Both color one gray will be presenting the useful insertion of the compensator. Uniaxially positive. Yes, this will be going to cross, this is going to cross, this is going to cross, and this is also going to cross. They are not in this particular direction. Similarly, the negative one, optically negative crystal or northeast, you can see now, parallel to the slow ray. Again, parallel to slow ray, parallel to slow ray. Yes, the parallel to the slow ray. So that is going to make out topic or interference phenomena in optic sign. I hope you may like this video. If you have any your suggestions or comments are there, I will try to solve this one, or I can make a videos on that and upload it on the YouTube channel. I hope this is clear. Thank you. Have a nice day.